Okay, this is APSTAT Chapter 8 review here. So a marketing consultant wants to estimate the true proportion of all residents that live near a certain mall who make at least one purchase at the mall in the past week. He stands at a mall exit for 2 hours on a weekday afternoon and flips a coin each time a shopper leaves. If the coin comes up heads, he asks them if they have made any purchase during this visit. After 2 hours, he has 132 responses, 104 of which make a purchase. Which condition for constructing a confidence interval proportion has he failed to satisfy? So number of successes is 104. So 104 is more than 10, so that works. 132 minus 104 is 28. 28 is the number of failures. That's more than 10. N is not a 30. That is not, that's for means, not for proportions. This is proportions, so that was a tricky one there. The sample size is at least 10%, or less than 10%, sorry, less than 10%. So there's probably a whole lot of folks that live near the mall. It's pretty ambiguous, but that seems to satisfy that. The one that's definitely in question here is this a random sample of the population of interest? So who are we studying here? So the proportion of all residents that live near a certain mall. So they're trying to, figure out how many of those residents, do this particular thing. Well, why are you asking people as they walk out of the mall? People who go to the mall don't necessarily live near the mall. You're not even really measuring the proportion that you're claimed to be measuring. So this one is definitely suspect. Is it a random sample of the population of interest? No, it's not sampling people who definitely live near the mall. 95% confidence interval from the mean of a population is computed from a random sample is found to be 9 plus or minus 3%, or 9 plus or minus 3. We may conclude that there is a 95% probability that mean is between 6 and 12. It's almost that, but that just seems a little off. I don't think it's exactly probability there. 95% of values are between 6 and 12. No, that's not really what a confidence interval is about. There's a 95% probably the true mean is 9 and 95% the true margin of error is 3. No, I don't think so. Definitely not that one. So if we select many random samples from each computed a 95% interval for mu for each of those, so many intervals, approximately 95% of those intervals, this is kind of the definition of interpreting the level there, that's what we're saying. So that's a really good definition of that. A researcher studying reaction times of drivers states that a 95% confidence interval for the mean time it takes a driver to apply the brakes after seeing the brake lights on a vehicle is between 1.2 and 1.8. What are the values of the point estimate and margin of error for this? Okay, so you're going to average those two numbers. You can add those up and divide by 2. So if you get your calculator out, if you want to, or you could just do it in your head. But you could go 1.2 plus 1.8 divide by 2. That's your point estimator. And then do that number minus one of the ends there, and that'll be your 0.3 would be your margin of error. So 1.5, margin of error 0.3 looks like this guy. A researcher studying the reaction time of drivers states that a 95% confidence interval for the mean time it takes a driver to apply the brakes after seeing the brake lights of the vehicle in front of us is 1.2 to 1.8, same scenario. Which of the following claims is justified? Okay, so reporter claims that any randomly selected driver would take at least 1.2 seconds. So any driver, that's not, we're estimating the mean. We're trying to capture the mean, so I don't think that one's about the mean. Let's try C. Reporter claims that it takes at least 2 seconds to apply the brakes after, again, that's not talking about the mean, so I don't think it's C. A reporter claims it takes 1.2 to 1.8 seconds to apply the brakes after seeing the brake lights. Again, not talking about the mean. Takes at least 1.5. That is the mean, but at least it could be less than that. So let's try this one. Reporter claims that the mean amount of time, oh, I like that, takes is at least 1.2. We think it's between 1.2 and 1.8, and we're pretty confident the mean is between there. So that's what we're saying. The reporter did a good job if they said that. That's good. I collect a random sample of size n from a population from the data collected and compute a 95% confidence interval for the population proportion. Which of the following would produce a wider confidence interval based on these same data? Okay, so I want a wider confidence level. So you get a wider confidence interval. Okay, so I want it to be wider. So I'm going to use a larger confidence level. That seems to work. This doesn't work for sure. Use the same confidence level, but compute interval n times, approximately, I don't know what that means. That's not the thing we do. Increase the sample size. That's going to make the confidence interval smaller, which we want it wider. No. Nothing can ensure that we get a wider interval, only say probability greater or larger is 0.05. Okay, so it's definitely A. In an opinion poll, 25% of random sample of 200 people said they were strongly opposed to having a state lottery. Okay, what's the approximate standard error? So the formula for standard error is square root of p hat q hat over n, I believe. So let's get our calculator out and see if we can calculate this. So if we do the confidence interval on the calculator, it doesn't actually do that for us. It kind of just tells you the margin of error, tells you the, all the other stuff, but it doesn't tell you the standard error actually. So that's when you might have to actually type it in. So it's a good question actually. Control divide. So p hat is 0.25 times q hat would be 0.75 over n, which was 200. Should give us a decimal 0.306. There it is. A newspaper conducted a statewide survey concerning the race for state senator. The newspaper selected a random sample of 1,200 registered voters. 620 of them planned to vote for the Republicans. A P equal the true proportion of all voters that voted for Republicans, which I thought gives the correct 90% interval. Okay, so let's actually just do this in our calculator. So we're going to do a confidence interval. So let me get this over a little bit further over here so we can kind of see a little bit more. Okay. So menu 665 is for one prop z intervals, which is what we're doing here. The number of successes is 620. This is not bad. 1200. It's easy. 90%, so 0.9 or 0.90. So our, let's see, our p hat is going to be 0.51. Well, it's 0.517 rounded because they're all that. Margin of error is 0.023, so 0.0237. Wow, I had to be careful there. 0.0237, which rounds to 0.024 there, so C. A large Midwestern university, a simple random sample of 100 entering freshmen in 2014, found that 20 finished at the bottom of their high school. So that's what, 20 out of 100 or 0.2. So that's where this is coming from in there. That makes sense. And then 10 finished at the bottom. That's where this is coming from. So the one proportion is 0.2. The other one is 0.1. They all have that. So that makes sense. It's 99% confidence. So right away we could figure out the well. You probably know it's not that because that's 95% confidence Z critical value. But in case you forgot how to do that, if you need to, so I did that wrong. I like to draw it this way. So you draw 99% in the middle, which means 0.5% over here and 0.5% over here. So if you're finding this Z critical value, to the left of that point is 0.995. So to figure that value out, you're going to go menu 653. The area is 0.995 to the left of the Z critical value. Just leave that 0.2, 0.576. There you go. So that's where that number comes from. We know that the proportions are 0.2 and 0.1, so they have to be 0.2 and 0.1 up here. They can't be whatever those are. I'm not sure why that is there, but we know it's D at that point, just by process of elimination, even if you don't hardly remember the formula. Okay, 9 students from a sample of 100 students at the University of Pittsburgh do not like to watch football. 5 students from a random sample of 100 students at Penn do not like to watch football. We like to calculate a confidence interval for p hat 1 minus p hat 2, or p1 minus p2, sorry. The true difference in the proportion of students from each of these 2 universities do not like to watch football. Which of the following conditions are met? There are at least 1,000 students at the University of Pittsburgh and at least 1,000 students at Penn State. Well, that seems true. I think that condition is met. There's a lot of students at both of those. Those are big schools. The counts of success and failures in each samples are at least 10. So there are 9 and 5 successes in each school. That is definitely not met. So I don't think 2 is being met. 2 independent random samples were taken. So they're random samples. They're both random samples. They seem independent of each other. That seems to work. So which of the following conditions are met? I would say 1 and 3 are met. The critical value used to construct a confidence interval for the proportion depends on the what? So we just did a critical value. Remember when we did this guy right here? All we were given is the confidence level of 99%. So confidence level is what we need. That's it. Okay, so now we're to this one. Okay, so quality control inspectors inspecting ball bearings made during a single day using a new process to determine the proportion of defective ball bearings. The inspector selects a simple random sample of 90 ball bearings from the 5,000 ball bearings produced on that day. After close inspection of each ball bearing, 11 were found to be defective. Construct and interpret the confidence interval for the true proportion of all defective ball bearings among those manufactured during the process. Okay, so we just want to do a regular old confidence interval. So you want to state, you want to start with that kind of stuff. Okay, sorry about that. Had a little trouble with stuff. Okay, with the technology, sorry about that. So 95% confidence level, P, and not P hat. We're talking about the parameter. The true is the true proportion of, and then you say this in context. So two portion of process to determine the proportion of defective ball bearings produced that day. So that's, I would say, in context. So I'm not writing it all down because it's hard to write on this screen. Okay. Okay, then you want to say the name of this. So this is a 1 prop Z interval. Then you want to check the conditions, right? So what are the conditions for this one? So we want to say that it's random sample. So you processed a simple random sample. Sometimes I even draw a line to this. So there's a random sample. The second condition is the less than 10% condition. So 90 ball bearings from the 5,000. So 90 is greater than or equal to 10. And number of failures, or so okay, 11 out of 90. So 11 was greater than or equal to 10 because 11 successes, they were defective, 11 defective, which means there were 90 minus 11 is 79 were good, actually, greater than or equal to 10. So we do have at least 10 successes. Less than 10% is, the next condition is less than 10%. So 90 is less than 10% of 5,000, which is true. 500 would be 10%. So 90 is less than 10% of that. So it checks all the conditions. So we're good to go on that. We're going to plug into the formula here. So p hat, we might need to get a calculator out. Okay, so p hat is, we just did that in the calculator, is 0.12 plus or minus z critical value. It's, let's see, do we know? Oh, 95% confidence, so 1.96 times square root of p hat, which is 0.12 times 0.88 all over n, which is 90. So I would show that part from scratch, and then I would go to the calculator menu, 665. The number of successes was 11 out of 90, and we wanted 95%. Just does all this for us. So nice. I usually start at the lower bound, upper bound at the bottom there, so 0.05, 4, I guess. No, maybe 5 to 0.189, so 0.19 is okay there. You rounded it. The margin, so this is 0.12 plus or minus the margin of error of, I'm just using the calculator results there, 0.068. So that's really good work there for the do. Conclusion, we are 95% confident that the interval from 0.055 to 0.19 contains the true proportion of defective ball bearings produced that day. Again, I didn't write it all down, but hopefully you're listening to that. You can check the enter key at the end to see if I missed anything slightly there, but that's the idea of it. Using the old process, the proportion of defective bearings was 20%. The plant manager claims the true proportion of defective ball bearings using the new process is different than 20%. Does the interval suggest that this claim is plausible? So 20%, is that plausible or not? Is that in the range of plausible values? So 5% to 19%, 20% is not in that range. So this is not, so we think this new process is effective. We think that we do have evidence to say that 20% is not in the plausible values. It's different, that it is different. So we agree that it is different from 20%. In fact, we think it's lower. So that's good, actually. So this new process is working, is basically what we're saying. We have evidence to say that it is. Great. A company that sells glassware to two manufacturing plants has two manufacturing plants. In a quality control inspection of random sample of 150 pieces of glassware from plant A, 8% of the pieces had defect. In a random sample of 200 pieces from plant B, 6% had a defect. Construct and interpret a 99% confidence interval for the true proportion in the portion of pieces from plant A that are defective, the portion of plant B that are defective. Okay, so we have to, confidence level is 99% confidence level, so we say that first. Then you say P hat, let's see if there's a meaningful, I just call them P1 or should I call them something? How about P sub A is the true proportion of, and let's talk about the context, of defective glassware from plant A produced on a certain day, I guess. And then P sub B is the true proportion of defective glassware produced from plant B, okay? So now we go to this next step. So we want to state, what is this? What is this test we're doing? This is a two-prop Z interval. So that's the name of this guy, right? So we want to check the conditions now. So the conditions for this one. Is it a random sample? So in a random sample of 200 pieces, so yes, random sample for both. So then we want to do less than 10%. So yeah, there were tons. Glassware manufacturer is going to produce a bunch, so just 150 or 200 is much. So 150 is less than 10% from plant A. 200 is less than 10% from plant B. Okay, number of successes and failures. So let's get out the calculator. So I may not write all this down, but you need to do this. So 150 times 0.08, 150 times 1 minus 0.08, whoops, 150 times 0.08, 150 times 1 minus 0.08. So those are number of successes, fails for A. They're both bigger than 10. That's good. 200 times 0.06 and 200 times 1 minus 0.06, which is 0.94. You can do it either way. Those are both at least 10. You would show that work on your paper. It's just hard to write in this thing, so I sometimes just tell you what you would write in the paper. Okay, so now we're ready to plug in our proportions. So the first one's going to be p hat 1 minus p hat 2. So, or p, I'm just going to specify. So this is going to be somewhere in your paper, you need to say, p of A, let's do p of A minus p of B. So that's helpful to know what we're doing here. We're going to do A minus B. So the proportions here would be A, which is 0.08, minus 0.06, plus or minus Z critical value. If you don't know that one, it is menu 653 point, oops, 65, 65, it's not responding, sorry, 653. Inverse normal is 0.995. Okay, so we get 2.58. 2.58 times square root of, and there's going to be a lot in here, so this is going to be 0.08 times 0.92 PQ over N, which is, for the first one, 150, plus, and if you need these formulas, they're on your formula sheet. So 0.06 times 0.94 all over 200. So that looks good. Now we're going to do this in our calculator. So menu, 666, so 6, 6, 6. So we want to do the A first because that's the order we did. Whatever you put first is that minus the other guys. So this one's going to be the number of successes was, let me see what they were. It helped to have these on your paper. 12. That was 12 and 12. So nice. Menu. So 12 out of 150, and then 12 out of 200. And it was not 0.95, it was 0.99, I believe. Okay. Okay, so we have all the data there. So this would be, the lower bound is negative 0.05, comma, 0.09. This is p hat 1 minus p hat 2 would be, so that's just 0.02 plus or minus. The margin of error, which is 0.0716. Beautiful work there that we've shown. And so then we're going to do, we are 95 or 99, sorry, 99% confident the interval from negative 0.05 to 0.09 of the true difference in proportions between the defective glass samples in proportion of defective glass samples in plant A versus the defective plant samples in, or the defective glass samples in plant B. Sorry, just takes a minute. There's a lot there. It doesn't have to be perfect, but you want to say difference in proportions. That's a key there. It's the difference with our normal interpretation and when we're interpreting a difference of intervals. Based on the confidence interval, is there convincing evidence the true proportion of pieces from plant A that are defective from the true proportion of plant B are defective? Is there a difference? So is there? So is 0 in the interval? 0 is in the interval. So we don't have enough evidence to say there is a difference between plant A and plant B. So we don't have enough evidence to say that. It doesn't mean it's not true. It just means we don't have the evidence from our sample there. Okay. Consumer Watchdog Organization estimates the true mean weight of 1 fun-sized candy bars to see if customers are getting their full value for the money. I like this. A random sample of 25 bars is selected and weighed, and the organization reports that a 90% confidence interval, their true mean weight, goes from 0.992 to 0.998 ounces. What is the point estimate of this sample? Okay, so this one seems like a much easier problem just in general. So let's see. So this is going to be 0.992 plus 0.998 divided by 2, 0.995. And I would add the word ounces to know that we are talking about the context here. We are talking about ounces. What is the margin of error? Okay, so you're going to take that number, the 0.995, and subtract either one. I do the lower one, 0.992. So I did not do that right. Okay, so subtract 0.992, 0.003, so 0.003. So we're talking about ounces here. Interpret the confidence level. So the confidence level is 90%. So if we took many samples and made many confidence intervals, about 90% of them would contain the true proportion of the true mean weight, the true mean number of ounces in the thing. Okay. A manufacturer of flashlights, and again, you can look down here to see the formal. So if we were to select many samples of size 25 from the population of fun-sized candy bars and construct a 90% confidence interval using each sample, about 90% of the intervals would capture the true mean weight of fun-sized candy bars. So that's the best description there. Okay, 14, last one. A manufacturer of flashlights wants to know how well their newer styles is selling in a chain of large home improvement stores. They select a random sample of 20 stores. How many of the flashlights were sold in a 30-day period and constructed a 95% confidence interval for the true mean number of flashlights sold? Explain what would happen to the width of the confidence interval if the confidence level were increased to 98%. So if I increase that confidence level to 98%, I need to increase the width of the confidence interval. You have to cast a wider net to make sure that that is, let's see if they said anything else for 14a. If the interval has to capture a true mean of 98% of the time, in repeated samples, instead of only 95% of the time, it will have to be wider. Increasing confidence level will increase the width of the confidence interval. How would you expect the width of the confidence interval to change if the flashlight manufacturer selected a much larger sample? So if the sample, instead of just sampling 20 stores, they did 40 stores or something, right? So what's going to happen? So that the width of the confidence interval is going to get much smaller. Larger sample size, you're going to have smaller. Let's see what they said. If the sample size is much larger, the standard deviation of the sample distribution will be smaller, so the confidence interval will be narrower. Increasing sample size will decrease the width of the confidence interval. Okay, that is your review for Chapter 8.